Hello everyone. Today we'll start with the part 5 of coordination compounds. In this video we'll discuss about crystal field theory. So in the previous video we have already discussed Werner's theory and we have already discussed VBT, that is valence bond theory. So as I explained in the previous theory, valence bond theory has certain limitations. Limitations were there. So to counteract those limitations, the crystal ball field theory was proposed. In this theory, first you need to understand how d electrons of these transition metals like 3D, 4D, and 5D transition metals form the coordination compounds. So how the d electrons get affected? The d electrons that we have is d dxy, dyz, dzx, dx square y square, dx square minus y square, and dz square. So first you need to know about the shapes. So let us say this is x, this is y. So dxy is in between. Okay, this is dxy. Let's say this is y axis and this is z axis. So dyz is in between, like that. The orbital shapes are dxz is in between those axes. This is dzx or dxz. Coming to the other two orbitals, that is dx square minus y square. These lie on these x and y axis. Okay. And the last one is dz square. Okay. This one is dz square. This is z axis. So, in coordination chemistry, we are dealing with metal complexes where d orbital is filled. So, considering these are the 5d orbitals and these are their orientation in the x, y, and z axis. When that metal ion is free, that means free metal ion, no effect on the energy of d orbitals. Energy of these d orbitals. That means all the five orbitals over here, these five orbitals that I explained, these dxy, dyz, dzx, dx square y square, x square minus y square, dz square, all these five orbitals have same energy. Okay, but as soon as ligand comes, ligand, let's say ligand, this was metal. Okay, this is metal and ligand comes in close proximity to this, what happens? The energy of the metal d orbital decays. Let me change the pen. So here you can see the energy of these 5d orbital decays, and they come with basically there happens a attraction. Whenever there is an attraction, the energy goes uh, basically energy decays, energy goes negative. So this was the initial energy, and when ligand comes, ligand has a negative charge, metal ion has a positive charge. Okay, the positive and negative electrostatic forces of attraction are there between. In crystal field theory, it is postulated that electrostatic force of attraction is there. Force of attraction between the ligand and metal. Between ligand and metal. So, when no ligands are present, the d orbitals have higher energy and they all are having similar energy. But as soon as the ligand comes in close proximity, their energy reduces. But even when but when it comes more closer, let's say metal and ligand initially was at having this distance, this much distance was there, but now the ligand is in close proximity. So what will happen? There will be repulsions. Metal has d orbitals, and the ligand has filled orbital. Ligand has negative charge, so these will repel. The so repulsion will occur. When repulsion will occur, so energy will increase. Okay, so energy will increase. Now there will be splitting of energy. Why energy gets splitted? There are five kinds of d orbitals. Okay, some d orbitals are in between the axis and some are on the axis. So those who are in between the axis, they will be repelled less. So dxy, dyz, and dzx, there will be less repulsion. But for dx square, y square, and dz square, there will be more repulsion. So, because more repulsion is there, that means when repulsion is there, energy increases. When repulsion is less, energy decreases. So, that's how splitting occurs. And depending upon the splitting and how much they are splitted, which is further dependent upon the ligand's attraction, uh, the orbitals are splitted, and further they affect the filling of the electrons in these orbitals, and that further affect the magnetic properties and other properties of the metal complex. I'll explain all this in detail. This was just the introduction. Further, I'll explain everything in detail, so please don't worry. So, for now, crystal field splitting basically defines crystal field splitting. The word suggests the splitting. Splitting here is of d orbitals. Why d orbitals are splitted? Initially, d orbitals were similar energy. Similar energy was their energy, but when ligands come, then energy will be increased. Energy increased, but since ligands are coming from different direction, generally in octahedral complexes, in octahedral complexes, what you see, this is an octahedral complex. Okay, this is metal with 6 ligands. So ligands generally come from the these directions, x, y, and z. This is x axis, this is y axis, and this is z axis. So ligands generally come from these directions. So those orbitals which are present on these axes will be repelled more, while the orbitals present in between the axes. So the d orbitals are fivefold degenerate. Degenerate means free and similar energy. Degenerate means similar energy. So initially the d orbitals are 5d orbitals are degenerate in the gaseous metal ion. If a spherically symmetrical field is of the negative ligand field charge is imposed, that means spherical symmetrical means symmetrically from all the directions, similar repulsion is there, similar attraction is there. Ligand is negative charge, metal is positive charge. And spherical symmetrical, that means all the orbitals will feel similar and will feel similar repulsion, will feel similar attraction, sorry, because metal is positive charge and ligand is negative charge, will feel similar attraction. That will cause a decay in energy. Decay in energy. Okay, the d orbitals will remain degenerate but followed by some changes in the energy of the free ion. Further, when more ligand will come more closer to the metal, then the negative charge present on the ligand will repel the electrons present in the orbital. So due to that repulsion, energy will increase, and depending upon the direction from which ligands are coming, there will be splitting of the d orbitals. So crystal field theory. Crystal field theory was proposed which described the metal ligand bond as ionic bond. In the VBT, they defined that metal and ligand bond is that covalent character has is there, covalent coordination bond forms. But here in the crystal field theory, they are saying that metal is positive charge, ligand is negative charge. So there is an electrostatic force of attraction between them. Electrostatic force of attraction between the ligands. Crystal field theory basically consider ligand as anions. as a point charges and neutral molecules as dipoles. So, when transition metal elements are not bonded to any ligand, that means this is metal. Metal has d electrons, d orbitals, sorry, d orbitals. So when no ligand is present, these d orbitals, the dxy, dyz, dzx, okay, and the other two dx square, y square, x square minus y square, and the last one is dz square. So this is zx. Let me draw the label the axis by different pen. This is x-axis, this is y-axis. So dxy is in between them. dyz, dzx, dx square, y square, x, y, and the dz square. Okay. So when no ligand is present, all the five orbitals dxy, dyz, dzx, dx square minus y square, and dz square, all these are similar energy. When they start bonding with the other ligand, okay, when they start bonding with the other ligand due to different symmetries of the d orbital, since you can see three are in between the three lobes in the three orbital lobes are in between the axis, and in two lobes are present on the axis. Inductive effect of the ligand, that means the negative charge present on the ligand, on the electrons, and metal has electrons in the orbital. So due to the inductive effect repulsion, the d orbitals split apart. There is a splitting of the orbitals. The dxy are in between dxy, dyz, and dz square. Dxy, sorry, dxzy. These are present in between, so they are repelled less, while dx square, y square, and dz square are present on the axis, so they are repelled more. Their energy is increased. Uh, so what I said. So metal, let's say metal. This is metal. Metal has dx square, y square. This is x-axis, this is y-axis. This is dz square. This is z-axis. Okay, this one. We have the xy. This is x-axis. This is y-axis. We have the yc. This is y-axis. This is z-axis. We have xc. This is x-axis. This is z-axis. So initially, the five orbitals were degenerate. That means same energy. Here is the metal, no ligand is present. But when metal comes, metal has ligand comes in spherically equivalent attraction from all the direction. That means ligand comes and there is enough distance that there are equal repulsion or attraction between the metal and the ligand from all the directions. Then the energy of the d orbital is reduced. Attraction means energy will decrease. Energy decreases. E decreases. So now it will be decrease. Now a stage will come, then metal and ligand are close. This is ligand negative charge, metal has positive n charge. Okay. Metal has some orbitals. Metal has orbitals, and those orbitals are different orbitals. So different orbitals. You can see now these 1, 2, 3, 4, and 5 d orbitals are present. So let's say an octahedral complex is being formed. Octahedral is formed like this, no? This is ligand, 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 ligand. Okay. So this is an octahedral complex. Let's say this is the x-axis, this is the y-axis, and this is the z-axis. Now you tell me, if ligands are coming from and forming an octahedral geometry, that means they are coming from x, y, and z directions. Those orbitals that are present on axis. Which orbitals are present on the axis? Here you can see this one, d dx square y square and dz square is present on the axis. So they will be repelled more, more repulsion. So the 5d orbitals which are present over here, these 5d orbitals, what will they do? These will again split. The 5d orbitals, the 1, 2, 3, 4, 5, these will again split. The one where the repulsion is less, that means more, less repulsion. Repulsion means energy will increase. And the one where repulsion is more, dx square, y square, and dz square, repulsion is more, so their energy will be increased. And the three, these three, where the orbitals are in between the axis, so their energy will decrease. The increase in energy and the decrease in energy occur by equal amount for the orbital, and the center is called the barycenter. Barycenter. So this is reduced by uh, some amount, and this is increased by some amount. We'll discuss that in detail in further slide. So crystal field splitting octahedral complex, as I said, in the case of octahedral coordination complex, six ligands surrounding the metal ion, we observe repulsion between the electrons in the d orbitals and the ligand electrons. So the repulsion is experienced by in the case of dx square y square orbitals, as metal has electrons in the orbital, ligand has negative charge, repulsion increases. Those orbitals that are present on the axis, that is z square, y square, and dz square, they observe more, more repulsion. More repulsion means the orbitals will split in like this. Dz square, x square minus y square will be up, dz square will be up, and dxy, dyz, and dzx will have less energy. Okay? The d orbitals will split like this. Hence, they have higher energy average in the spherical crystal field. Similarly, the other dxy and dyz and dzx orbitals experience lower repulsion, so they are directed as they are directed in between the axes. As they are directed in between the axis, and ligands are coming from the direction of axis. They are coming from the x, y, and z directions. Since they are present in between the axis, so the repulsion is less. Hence, these three orbitals have less energy than the average energy. Therefore, the repulsion in the octahedral compounds yield two energy levels. The upper two, these upper two are called T2G levels. These upper two are called T2G, and the lower three are called EG levels. The upper one is called EG and the lower one is called T2G levels. Okay, so this is how the splitting occurs. The 5d orbitals are present over here. These have same energy. When ligand comes, splitting occurs. dxyz square goes up, and 3 dxy dyz and dzx goes down. The increase is energy is by 6 dq, or you can say zero point 0.6 delta naught. 1, 1 delta naught is equal to 10 dq. Okay, and the decay in energy is by 4 dq, negative 4 dq. It is positive 4 dq, or you can say minus 0.4 delta. This is the splitting in octahedral fashion, octahedral complexes, and the difference is called delta O, crystal field splitting energy. This delta O is called crystal field splitting energy. Okay. The splitting energy of the degenerate levels in the presence of a ligand is known as crystal field splitting. As I said, D generate orbitals splitted in the presence of the ligand like this, and this is called crystal field splitting. The difference between the two energy levels is denoted by delta O. This is Eg level, this is T2G level, this is dxy, dyz, dzx, this is dx square minus y square, this is dz square, and the delta is denoted by uh, the energy gap between them is denoted by delta O, that is crystal field splitting energy. Splitting energy. Some ligands tend to produce stronger fields, thereby causing the large up. So, since this splitting occurred because of the electrons in the d orbital and the ligand negative charge. So, those who are strong ligands, tend to cause more splitting. More splitting. So, strong ligand will cause more splitting. So, the delta O naught value will be more. And the smaller or weak ligands will cause smaller splitting. Coming to the high spin and low spin complexes, as you have already seen that strong ligands cause more splitting. This delta note will be more. Okay. And weak ligands will cause less splitting. This delta note is less. This one is more. So, if the filling of electrons is to be judged, that means those where electrons the splitting is less, the electrons can easily be filled in the higher levels. Okay, but if the splitting, this delta on that note value is more, then there could be like uh, double filling of the orbital. So overall we can say if delta note is less, then there will be high spin complexes. High spin means more number of unpaired electrons will be present. But in the case of strong filling ligands, since the delta note value is more, so there will be more pairing of the electrons in the lower energy orbitals. So the unpaired electrons are number of unpaired electrons will be less. That will cause low spin. Okay. So the complexion with the greater number of unpaired, the complex ion, it is basic complex ion with a greater number of unpaired electrons is known to have high spin. So here in the less splitting case, the number of unpaired electrons are more, so it is a high spin complex. And the low spin complex contain lesser number of unpaired electrons, as you have seen in the case of more splitting. High spin complexes are expected with the weak field ligands. High spin, as I told, weak ligands cause less splitting, and that will form high spin complexes. Whereas the crystal field splitting energies, where the crystal field, this delta note is small, no, delta note is less. The opposite applies to the low spin complexes in which the strong field ligands, if I am using strong field ligands, more splitting will occur. More splitting will occur. That means the filling of electrons will be include the pairing, and pairing of electron means less number of unpaired electron. Less number of unpaired electron means low spin complex. Okay. So coming to one example, let's solve this question. Cobalt cyanide 6 3 minus. Find out the oxidation state of cobalt. X minus x plus 6 into cyanide has a charge of minus 1, total minus 3. X minus 6 is equal to minus 3, x is equal to minus 3 plus 6, x is equal to plus 3. Cobalt has an electronic configuration 3d74s2. So cobalt 3 plus will be having 3d6. Okay. Now you have 6 electrons present in the d orbital. 1, 2, 3, 4, 5 and 6. Okay. As the ligand is strong, So the delta note value will be more. Delta note more. So delta note is more, then what will happen? It will be like the filling of electrons will be in the lower orbital only. We need to fill six electrons. 1, 2, 3, 4, 5, 6. 6 electrons are filled in the T2G orbital only. EG is empty because delta note is more, electrons can't be filled in the higher energy orbitals. But in the case of cobalt, F6 3 minus x plus 6 into minus 1 is equal to minus 3. Oxidation state will come out to be plus 3. Here, fluoride is a weak ligand. So, filling of 6 electrons will be like 1, 2, 3, 4, 5, 6. When splitting will occur, delta note is less. This delta note is less. Okay. So, the filling of electrons will be 1, 2, 3, 4, 5, 6. First, the singly all orbitals will be filled in a single filled fashion only. Here you can see number of unpaired electrons in the case of cyanide. Number of unpaired electrons are 0. Here in the case of weak filled ligand fluoride minus, number of unpaired electrons are 4. That tells in case of strong filled ligands, low spin complexes form. In case of weak field ligand, high spin complexes form. Spin is high, no number of unfilled electrons are 4. So each electron has a spin of 1 by 2. So total spin will be 4 by 2, that is 2. Here the spin will be 0. I hope you understood what I am trying to say. That in cobalt, cyanide 6 minus this thing, and cobalt F6 3 minus, the splitting will be like this. Okay, 2, 3, 4, 5. Here the splitting is like this. So where delta note is more? In case of here, delta note more. Here, delta note less. So the filling of electrons, since that electrons, we have 6 electrons over here for cobalt 3. Cobalt 3 is here, cobalt 3 is here. Cyanide is the strong ligand. Fluoride is a weak ligand. So less splitting. Delta note less. Therefore, electrons will be filled in the higher energy orbitals like this. So total unpaired electrons are more. More unpaired electrons. That means high spin. Here all the 6 electrons will be filled in the lower energy orbitals because the gap is too high. Electron can't jump from here to there. T to G only electrons will be filled. So strong ligand, more splitting, delta note more, less number of unpaired electron, less unpaired electron. That means low spin. You understood? So here you can see in the case of cobalt cyanide complex, all the electrons are filled in T to G. In the case of cobalt hexafluoro complex, not all the electrons are filled in T to G. Electrons are first filled singly in all the orbitals and then it started pairing. So here you can see delta note for cyanide is more, delta note for fluoride is less. So here we can say that cobalt cyanide is a low spin complex, and cobalt fluoride is a high spin complex. Coming to the crystal field splitting in tetrahedral complexes. So what was the difference in a tetrahedral complex and a octahedral complex? In case of octahedral complex, Six ligands are coming. Six ligands are there, and these ligands coming from the direction of x, y, and z axis. While in the case of tetrahedral complex, you can say these orbitals, these ligands are coming in between. Ligands are coming from the direction in between the axis. Okay, so basically, let me draw the axis for you. Let's say this is the z axis, this one is the z axis, this one is the y axis, and this one is the x axis. Here you will see the direction of axes are different. Okay, so these are the direction x, y, and z. Ligands are coming in between the axes. We have five kinds of orbital. Here you saw that the splitting occurs such a way that dxy, dyz, and dz square, dxy, zx went down, and dx square minus y square, dz square went up. Because the ligands were coming from the direction of axis, so the orbitals present on the direction of axis, their energy was increased. But in the case of tetrahedral complexes, reverse thing happens. The orbitals present in between the axis, their energy is increased, and while which are present on the axis, their energy is reduced. Okay, so here dxy, dyz, and dzx, these will feel more repulsion from ligand. That's why the order of splitting is reversed. In case of tetrahedral complexes, the T2 orbitals, three T2 orbitals, that is dxy, dyz, these others, those orbitals, their energy is increased, while while the dx square, y square, and the dz square orbital, their energy is reduced. I hope you understood. So in the splitting of the five-fold degenerate d orbitals or, of the metal ion into two levels in a tetrahedral crystal system is the representative of the two sets as TD. So we have 5d orbitals. The orbitals present in between the axes, their energy is increased. dxy, dyz, dzx, their energy is increased, and the splitting is called delta TD, delta T, or we can say delta tetrahedral TD. So the electrons in the d square y square and dz square will feel less repulsion, so there will be more attraction, so their energy will be less, and the energy of the dxy, dyz, and the dzx orbital will increase. That as of dx square y square and orbitals are gold. There are only four ligands in the tetrahedral complex, therefore the total negative charge of the four ligands and has a ligand field is comparatively less as compared to the octahedral complex. In case of octahedral complex, you saw that splitting will give you delta O. Crystal field energy splitting in the case of tetrahedral complex will give you delta TD, delta T. Since only four ligands are there in case of tetrahedral complex, in case of octahedral complex, you have six ligands. So splitting will be more. delta O will be more than delta T. Okay. The direction of orbitals, the direction of orbitals does not coincide with the direction of the ligand's approach to the metal ion. Here, as you can see, the does not coincide as by this it means that since ligands and metal orbital that dxy, dyz and dzx are not exactly same, therefore delta t is less. There are two reasons for delta to be less. First is delta O octahedral is for 6 ligands and delta T is for 4 ligands. The other reason is delta O is exactly on the axis. The ligands and the metal orbitals present exactly on the axis. They are repelling each other. While in case of tetrahedral, they are not exactly on axis. Not exactly in similar direction. Coming to the third, the splitting pattern, here you can see the orbitals dx square y square went down. So the negative energy will be minus 6 dq, and the dxy and dz square, dxy, dzx and dyz increase. So the energy is raised by plus 4 dq. The splitting is called delta T. This is called crystal field splitting energy in tetrahedral complexes. Okay. Here you can see that the repulsion in the tetrahedral coordination compound yields two energy levels. Lower one is called T2 and the upper one is called E. Here we do not use D. Do not use G because G defines center of symmetry. In the case of octahedral complex, you have a center of symmetry. See, this ligand and this ligand are directly opposite each other, whereas in the case of tetrahedral complexes, behind this ligand there is nothing. So there is no center of symmetry in the case of tetrahedral complexes. That's why it is only written as T2 and E, not G. G word will be not be used in the naming of the orbitals. Coming to the crystal field splitting in the tetrahedral complexes is intrinsically smaller. Why delta O is greater than delta T? Two reasons. One, delta O octahedral has 6 ligands, while here 4 ligands are there. So repulsion is less. Other reason is that ligand and metal orbital directions same. Ligand and metal orbital direction not exactly same. Not exactly same. So they, because only two-thirds as many as ligands and they have less direct effect on the d orbital, the relative destabilization energy of the set will be minus dq and the destabilization effect of the T2 will be plus 4 dq. We have already seen. So the d orbitals are splitting like this. So destabilization energy for the dx square, y square and dz square is minus 6 dq, and for d x y and d y z and d z square, the stabilization energy is plus 4 dq. Coming to the crystal field stabilization energy, that is delta naught. In the chemical environment, the energy level generally split as directed by the symmetry of the local field surrounding metal ion. The energy difference between the Eg and the 2G levels is given as this energy difference. We have the splitting over here. This energy difference between the Eg and T2G, or we can say in the case of tetrahedral, T2 and Eg, E, not G. So This is called delta naught. This is called delta T. So this splitting is defined as 1 delta naught is equal to 10 dq. Okay? It states that each electron that goes into the lower T to G level stabilizes the system by an amount of minus 4 dq. So this one was uh, minus 4 dq, and the above EG were destabilizing it by plus 6 dq. In the case of tetrahedral complex, destabilization is by minus 6 dq and destabilization is by plus 4 dq. Okay. For example, the net change in energy for D5. Let's say you have a complex having D5 electrons. Okay. Fill the electrons in the splitted energy levels. Let's say we are putting energy we are putting electrons in the octahedral complex. So the splitting pattern will be Eg and 2 T to G. So D5 electrons, 5 electrons you have, 1, 2, 3, 4, 5. Fill these electrons 1, 2, 3, 4, 5. Calculate the delta naught. Delta naught will be 3 electrons in lower energies, that is minus 4 dq, plus 2 electrons in upper energy, that is 6 plus 6 dq. So 3 fours are minus 12 dq plus 2 electrons in upper T to Eg orbital. So it is plus 2 dq, 12 dq. So minus 12 plus 12 will give you 0. So for D5 and D10 systems, the then this splitting energy will come out to be 0. Let's see for the case of D10 as well. So for the case of D10, we have 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say we are forming a high spin complex or low spin complex. It doesn't matter in the case of D10. So you need to fill Eg to T to G. We are considering an octahedral complex. So fill the 10 electrons 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now calculate the delta naught. Delta naught is equal to 6 electrons in minus this D to G orbital, and energy is minus 4 dq. So minus 4 dq plus 4 electrons in upper direction where the energy is plus 6 dq, plus 4 into plus 6 dq. Calculate the value. 6 fours are minus 24 dq plus 6 4 6 are 24 dq. So these 24 minus 24 got cancelled. Delta naught is 0. So for D5 and D10, that's how for high spin complexes we calculated the value. Coming to the crystal field stabilization energy table, here you can see the different cases. I'll solve 2 3 examples for you. So let's see. First we'll solve high spin complexes only. So for the case of high spin complexes, starting with the D1 configuration, I am solving for octahedral. You please try to solve it for tetrahedral. So octahedral high spin complex. How will you solve it? Let's say I have degenerate orbitals having degenerate, that means same energy. Okay, splitting occurred. T to G went down in the case of octahedral. Splitting is like this only, na, and EG went up. Okay, so only one electron needs to be filled. dxy, dyz, dzx. Only one electron needs to be filled. Delta naught will be 1 into T to G is lowered by how much amount? Minus 4 dq. It is minus 4 dq. How many electrons are present in EG? 0. 0 into plus 6 dq. So what is the value? Minus 4 dq. Delta naught is equal to minus 4 dq for 1 electron. If you are having 2 electron system, let's say 1, 2, how will you fill the electron for the case of high spin complex? 1 and 2. Two electrons will be filled like this. So delta naught will be two electrons in minus 4 dq with having minus 4 dq energy. These are having minus 4 dq and this is plus 6 dq. So and 0 electrons in orbitals having plus dq energy, plus 6 dq energy. What will be the value? Minus 8 dq. Okay, delta naught is equal to minus 8 dq. I hope you are understanding. Let us say for the case of D3 complex. In the case of D3 complex, 1, 2, 3 electrons I am having splitting occurred. 1, 2, 3. Splitting is like this. So, what will be the delta naught value? Please do try to calculate it by yourself. Delta naught is equal to 3 electrons having an energy of minus 4 dq. This is the Berry center and the energy is lowered by minus 4 dq and the dx square y square energy is increased by plus 4 dq. This is Eg, this is T2G. Okay, 0 electrons in Eg. So the energy is minus 12 dq. In the case of D4 system, I have 4 electrons. 1, 2, 3, 4. Okay. Let's say splitting occurred. Octahedral splitting occurred. This is T2G, this is EG. Now 4 electrons need to be filled. There are two cases. One is high spin, other one is low spin. If it is in high spin complex, electrons will be filled like gap is more. High spin means strong ligand, delta not more. So what will happen? Weak ligand, sorry, weak ligand delta not less. So 1, 2, 3, 4. 4 electrons will be filled like this. But if it is a low spin complex, that means a strong ligand delta not more. So the gap is more here. As you can see, the gap is more than that. This gap is more. How will be the electrons filled? 4 electrons need to 1, 2, 3, 4. 4 electrons 1, 2, 3. Instead of filling the upper Eg level, it is filling only the downward only. So 4 electrons in the T2G and 0 electrons in the Eg. Now calculate the delta naught. Delta octahedral will be 4 electrons with minus 4 dq plus 0 electrons with plus 6 dq. Okay, it will come out to be minus 16 dq. But here if you calculate in the case of high spin complex, delta O naught will be 3 electrons with minus 4 dq plus 1 electron with plus 6 dq. Minus 3 for the 12 dq plus 6 dq, it comes out to be minus 6 dq. So compare the value. In the case of D4 system, that is 4 electron system, if the complex is a high spin complex, the value comes out to be plus 6 dq. In the case of low spin complex, the value comes out to be minus 16 dq. This is minus 6 dq. So, which one is more stabilized? Tell me. The one with lower energy is obviously more stabilized. So the one with lower energy is minus 16 dq. The low spin complex is more stabilized. I hope you guys understood. I will tell you one more example for this. The high spin and low spin variation. Let's say we have D6 system. D6. Okay. One side I'll draw a low spin complex. Low spin, that means a strong ligand, more splitting. Other side I'll draw a high spin complex, that means a weak ligand with less splitting. Here, the case of low spin complex, there are more splitting. In the case of weak field complex or weak ligand, there is less splitting. Okay, you have 6 electrons to be filled, 1, 2, 3, 4, 5, and 6. Since the gap is more, so how will be the filling occur? All the 6 electrons, instead of going up, all the 6 electrons will be filled in the downward orbital only. While in the case of weak field ligand, since the gap is less, so all the orbitals will be filled singly first. Filling will be like this. This is the EG, this is T2G, this is T2G, this is EG. Now calculate the delta note. Delta note. Delta note is equal to 6 electrons with minus 4 dq plus 0 electrons in the plus 6 dq level. It comes out to be minus 424 dq. Delta note for this high spin complex is 4 electrons in minus 4 dq plus 2 electrons in plus 6 dq. 4 4s are 16 minus 16 plus 12 dq. The value is minus 4 dq. Which one is more stable? Tell me. Which one out of both is more stable? The one with more negative value is more stable. This is 24 dq, this is minus 4 dq. So the low spin complex over here is more stable. Now tell me, are there any unpaired electron present? No. Here unpaired electrons are present. That's why it is called high spin. Each electron has a spin of 1 by 2. 4 unpaired electrons has a spin of 4 into 1 by 2. That is 2. S value is here over is 2. Here S value is total spin is equal to 0. You got it? Good. Let us move to the next topic, that is so we understood that depending upon the strength of the ligand, splitting happens. So depending upon how much splitting happens, we have made a spectrochemical series that defines their splitting strength. Okay. So some ligands are weak. We are saying ligands weak and strong. Weak and strong depending upon the splitting they caused. Splitting they caused. So we have made the crystal splitting depends on the field produced by the ligand and the charge on the metal ion. An experimentally defined series based on the absorption of the light by the coordination compound. This series splitting of the they have calculated by experimental method. Okay, experimentally they have calculated the magnetic moment, that is mu, and the absorption pattern of the electrons of the light. They have made this experimental designed series called a spectrochemical series. This is the spectrochemical series where you can see the halogens over here. Halogen, this one also halogen. Halogens are weaker ligands. Halogens weak field ligands. Then oxygen donating ligands. These are O donors. This oxalate, H2O, and hydroxo, these are O donor ligands. Then we have nitrogen donor ligands. This the ammonia, EDTA, ethylene diamine. We have N donors, and then we have pi acceptor ligands, carbonyl, cyanide, etc. Okay, NO we also have NO. So we can say halogens. Then halogens we can say to easily remember the series we can consider halogens, then O donor ligands, then N donor ligands, then pi acceptor ligands. Pi acceptor ligands include carbonyl, nitrosyl, etc. So coming to the pairing energy now. So the filling of the electrons, as I said, electrons filling in the higher energy orbital or the lower energy orbital, apart from the splitting, that is delta O, it is also depend upon the P, that is pairing energy. Pairing energy is the energy released when electrons are paired in an orbital. As I told in the case of D4, we saw that splitting could be, filling could be like two ways, 1, 2, 3, 4, or splitting could be like 1, 2, 3, and 4. All the 4 in T2G, 3 in T2G, and 1 in EG. So, what depends upon the this? The one factor that depends in is delta O, this splitting, delta O. The other factor that depends is pairing energy. Pairing energy is the energy release. Here, the pairing energy is released. Electrons are paired in this orbital, no? So the pairing energy is released over here. Filling of the d orbitals take place in the following manner. If the first three electrons are arranged in the T2G level, as per the Hund's rule, the fourth electrons can either go into the T2G level. As I said, it could either go in the T2G level, giving a configuration of T2G4, EG0, while or it could enter into the EG orbital, giving a configuration T2G3, EG1. Depending upon the magnitude of the crystal field splitting, that is delta O naught, and the pairing energy. This can be explained as, if say if delta O naught is greater than pairing energy, that means there will be pairing of electrons. There will be pairing of electrons. If pairing energy is greater than delta naught, then that means electron will be filled in EG orbital. Okay, here you can say that electrons enter in the T2G level, giving a configuration T2G4 EG0. Ligands producing this configuration are known as strong field ligands, as the delta or naught value is greater than pairing energy. While in the case of where pairing energy is greater than delta naught, electrons enter in the EG level, giving a configuration of T2G3 EG1. Ligands producing this configuration are known as weak field ligands and the form of high spin complexes. Coming to the limitations of crystal field theory. So, crystal field theory limitations. We have already discussed Werner theory, we have discussed valence bond theory. Now we are discussing crystal field theory. The theory defines in the BBT we said no, there we said basically they said that the coordination covalent coordination bond forms, and that too is a covalent nature. Both metal and ligand give electrons, share their electrons and form a covalent bond. But in the crystal field theory, they said that a bond is completely electrostatic, and there in this theory they explain the strong nature and the weak nature of the ligands depending upon the amount of splitting of the d orbitals. So that is a plus point of the crystal field theory. But even though it is better than the Wallace-Bourne theory, it contains certain limitations, that are the assumption that interaction between the metal and ligand is purely electrostatic. This can't be said very this cannot be very realistic, because in the previous theory VBT they said the covalent bonding is there. In this they are saying it is purely electrostatic, so it cannot be believed that is purely electrostatic. It needs further proofs. The other theory is that only d orbital of the central atom taken in the account, the s orbital and p orbital are not considered for the study. In the CFT, in the crystal field theory, you are seeing only that d orbital is splitting. D orbital is splitting here and here, or you can say T2G is going up or EG is going down. In the case of tetrahedral complexes, in the case of octahedral complexes, only d orbital are considered. While in the case of VBT, if you remember, we have d orbital, we have s orbital, and we have p orbitals. So there we saw that hybridization occur DSP 3D 4S 4P. We saw two type of complexes: inner field complexes or outer field complexes. There we studied hybridization sp3d d2sp3 or sp3d2. There we were studying the hybridization of orbitals, and we were taking into account the s and p orbital. In the case of CFT, we are only considering the d orbital case. So that is a limitation, like why we are not considering s and or p orbital. The third field is the to explain the behavior of certain metals which cause large splitting while others show small splitting. For example, there is no explanation why H2 is stronger as compared to hydroxide. H2 is a neutral ligand. Hydroxide is a anionic ligand. Anion should repel an electron more than a neutral ligand. So why H2 is a stronger ligand than hydroxide? They couldn't explain it. The other drawback is the theory rules out the possibility of having a p bonding. They are only saying that is an electrostatic bonding. They didn't p bonding, they didn't define the back bonding, and the pi character they couldn't explain. Pi character they couldn't explain. The fifth limitation is that the theory gives no significance of the orbitals of the ligand. Therefore, it cannot explain any property related to the ligand orbitals and their interaction with the metal orbitals. They are just saying that metal d orbitals, their direction they are considering. They are not considering the direction of the ligand having ligands orbital. They are not even mentioning that. They are just saying that ligands are coming from the metal orbitals direction or not from the metal orbital direction. They are not saying anything about the direction of the orbitals of the ligand. So that is another drawback for this. So that is what we discussed today. That we discussed CFT, crystal field theory. We discussed that in the crystal field theory they are defining the purely electrostatic forces of attraction, electrostatic pure between metal ion and the ligand negative charge. We understood the degeneracy of the d orbitals if metal ion is free, and when ligand comes the energy gets reduced, and if ligands come more closer then the energy levels get splitted. Depending upon the four ligands are coming, then tetrahedral splitting occurs. If six ligands are coming, octahedral splitting occurs. In the case of tetrahedral, we see the splitting like this. We see the splitting like T2 goes up, E goes down, and in case of octahedral, the reverse happen. EG goes up and T2G goes down. We understood about the crystal field splitting energy, that is delta naught. It is equal to 10 dq. It is basically the difference between the splitted levels difference. And we understood how high spin, low spin complexes are made, and and how ligands nature of causing the splitting defines that. Strong field ligand make low spin complexes, weak field ligand make high spin complexes. We understood about the pairing energy and the relation between delta naught and P. to affect the high spin and low spin nature of the complex. We understood about the electrochemical series of the ligands, which is completely experimental depending upon the experiments performed on the magnetic value and the absorption value obtained for the certain complexes. They defined the series where the halogens are considered as are considered as weak field ligands, which are weaker than nitrogen oxygen donors, which are weaker than nitrogen donors, which are weaker than carbonyl, NO, cyanide, etc. So we understood about that, and we further understood the limitations of CFT, limitations of CFT, that is, it is considering only the electrostatic forces. It is not talking about the p and s orbital. It is not talking about the orbitals of the ligand. So we understood all these factors. So thank you for watching. This is all for today. Bye.